Hi, welcome to my video. Today I'll be working through part 1 of exam 2 for my Transport 2 class for Mr. Co. In this video, we will be doing a dimensional analysis using the Buckingham Pi method to work through and identify our dimensionless groups before we go in and do the coding to make it a lot easier so that we can simplify the code by not having so many variables go into the mix. And so, diving into the problem, we are given a double-sided pipe where we have liquid flowing in down the sides of these pipes and gas going up the pipe. And really the first thing we got to do to start the dimensional analysis using the Buckingham Pi method is we got to identify the variables that we have. And so for the problem, we are giving the mass transfer coefficient, the velocity, the density, the viscosity, the mass diffusivity of fluids A and B, and the diameter of the pipe for the problem. And so the units of these in corresponding order as well is meter per second, kilograms per meter cubed, kilogram per meter second, meter squared per second, and meter for diameter, because why not? That's a simple one. The next thing that we're going to be doing before we actually start doing the Buckingham Pi method is that we need to construct a dimensional matrix using these units. And pretty much how we go about making this dimensional matrix is that we are going to be looking at what powers each of these units will be raised to, corresponding with the kilogram, meter, and second. And so that kilogram, meter, and per second are the rows of the dimensional matrix, and the columns are the actual variables themselves corresponding with which units they use. And so, say for example, we'll look at the mass diffusivity constant first, or mass transfer coefficient, sorry. But because that's meter per second, there's no kilograms, so that will be a 0. The meter is in the numerator, so it's meter to the first power, and that is a 1. And then the second is in the denominator, which if we wanted to move that to the numerator, that'd be seconds to the -1 power. And that's pretty much how we go about doing the dimensional matrix to solve this. And so I'm going to go through and look through the rest of these. Velocity is going to be the exact same because they're the exact same units. Density is going to have a 1 in the kilogram, a -3 for meters, and 0 for seconds. Viscosity is going to have a 1, -1, -1. The mass diffusivity constant from fluids A to B is going to be 0, 2, -1. And the diameter, once again, is the easiest one because it's only a meter, so it'll be 0, 1, 0. Now, the next thing we got to do before we actually once again go do the Buckingham Pi method to really solve and find our core groups and our dimensionless groups, we need to identify how many core groups we really need to come up with to characterize the situation that we were given. And so to find that, that's going to be what we need to calculate to find how many core groups we really need to use, is equal to the number of variables given, which is going to be 6, and minus the rank of the matrix. And I'm going to go through and I'll explain in the coding part of the video how we really found the rank of the matrix. But pretty much how we go about that is we got to import numpy as MP. When we do this, we bring in a linear algebra library that we can then use a rank function after we input the matrix into a variable of itself. We use that rank function and that will give us what the rank value is. And I'll go through do that in the coding part once again. But just to save time and to save a little time for me editing, don't really want to do it. I know that rank is going to be 3. And so once we do the 6 minus the 3, which is the number of variables minus the rank, we know that we need 3 core groups for the Buckingham Pi method. And so next thing we need to really do is we need to figure out which of these 3 variables we're given, which ones should we use as those core groups to set up the Pi method. And so we are going to be having Pi 1, Pi 2, and Pi 3. Alrighty. And so the first one that we're going to have to use as a core group is going to be the mass transfer coefficient, which is going to be Kc. This is really because this is not a characteristic of the fluid. Rather, it's something it's a value that you have to obtain by experimenting and doing multiple experiments to identify what that number should be. So that's probably the best reason why we should use that first, because it's not something that we can find, nor is it given. It's something we have to conduct experiments to find. The next core group that we're going to use velocity for Pi 2, And this is really just because it shares the same units as the mass transfer coefficient, which is going to be meters over seconds. And then for the third one, we are going to use viscosity, which in my opinion is just the easiest one to use because it has one of each variable in it. So it will help really just identify the dimensionless group. And so now that we have the 3 core groups identified and which ones we want to use, we need to go through and input the rest of the variables that we did not use into each of these equations. And so we will have the mass diffusivity constant from A to B in each of these. And then we will also have the density, and we will have the diameter, since those are the last 3 variables that we did not use as core groups. And since we have each of these, they're all going to be raised to a power, because we want each of these pi's really to be a dimensionless group. So we're going to have to raise each of these variables up to a power to really get it to be a dimensionless group and equate out to 0. And so we will have variables to take up these for right now. We'll use A, B, C, D, E, F, G, H, I. And now that we have these variables and what we really need to find, we are going to do something very similar to what we did over here by using the units that we have given to go through and find out really what these powers should be, these exponents. And so we'll go through and do pi 1, for example. So pi 1 is given to us as the mass transfer coefficient, which is meters per second, multiplied by the mass diffusivity constant between A and B, which is meters squared per second. We have the density of it, which is kilograms per meter cubed. And we have the diameter, which is just meters. And so by looking at this, we're going to be once again doing an analysis by the meters, kilograms, and the seconds to find out what A, B, and C should be equal to for this equation. All right. So looking at this, you don't actually look at the core group for when you're doing this analysis. It's just not something you do, and it will throw off what your values will be. And so instead, we'll start looking at the mass diffusivity constant from A to B, which is meters squared per second. And so we will have, sorry, I'm staring at the time. So we will have for M, it'll be 2A minus 3B plus C equal to 0. I think it's 1 plus. Yeah, it is 1 plus. I'm wrong. That's something I forget sometimes, and you got to understand that you do actually have to use that first value, because it actually does not make sense. That's a mistake on me. I correct myself. So now that we have this system of equations really to go through and solve A, B, and C. We cannot really solve this one right away. So we will go on and look at the kilograms. There's no kilograms here, there's no kilograms here, there's only 1 kilogram here. So it will be 1B equal to 0. So now that there's nothing really to equate this out, we know B is equal to 0. So that's really one solved, and we can take that one out of that equation because B is equal to 0. Now the last one we have to do is look at the seconds, and once again it's going to be -1 minus 1A equal to 0, and A is going to be equal to -1. And so now that we have these values, we can again go through and find C, where this will be equal to -1 plus C equals 0, and C is equal to -1 as well. And so that's very helpful with what we wanted to do. And now that we have the values of the coefficients the exponents in pi 1, we can rewrite pi 1 as Kc mass transfer coefficient multiplied by the mass diffusivity constant raised to the -1 power multiplied by the density, which is to the 0 power, so that's nothing, and then the diameter raised to the -1 power as well. That is actually incorrect. That is +1. That's my bad. It's a brain fart. So that's actually going to be d to the first power rather instead. And so this is actually going to be rewritten as kc multiplied by the diameter over the mass diffusivity constant from A to B. And this is going to be given as your Sherwood number. And that's going to be pi1 there. That's your first value that you really need. And so now that we have this, and we know that pi2 has the exact same setup and the exact same units as pi1, we know that actually A is equal to D, which is equal to -1, B is equal to E, which is equal to 0, and C is equal to F, which is equal to 1. And so really we can also rewrite pi2 real quick as pi2 equal to velocity. That's really the only difference between pi2 and pi1 is because we're using velocity rather than the mass transfer coefficient. So it'll be velocity multiplied by dAB once again to the -1 power, density to the 0 power, that'll be cancel out, and d to the 1 power, first power again. And so this will pretty much be the exact same thing with velocity, diameter, mass diffusivity constant A to B. Excuse me. And this is your Peclet number. That is going to be equal to pi2. And really, we got for pi1, we got pi2. The last thing we got to do is really just do the exact same thing for pi3. And so pi3, we'll write this out right here just to make it a little easier, which is viscosity. So viscosity, once again, is kilogram over meters second, which will be here. Then we have meters squared second again, kilogram meters cubed again, and meters. And so this right here is the units that we will have for pi3 here. And so really we'll set up the same exact system of equations for mass, kilograms, and seconds. And for pretty much the first one is going to be -1 plus 2a minus 3. I guess I don't use a actually anymore. It's g minus 3h plus I is equal to 0. Going on to the kilograms, it's 1 plus 1, which value is it? H is equal to 0. So we actually know that H here is equal to -1. And seconds is the last one, so it's -1 minus 1 g. And that's also equal to 0. So we'll add g to the other side, and g is equal to -1 as well. And so now that we know that h is equal to -1, g is equal to -1, we can then use these to go through and find the value of I. And so plug in -1 for g, -1 minus 2 is equal to -3. Plug in -1 for h, is that it's +3. We actually have I equal to 0. And so now that we have the exponential values for g, h, and I, we can go through and find the equation in the dimensionless group for pi3, which will be viscosity, the mass diffusivity from A to B, which will be going with g is -1, density, which will be going with h is also -1, and d, which is 0, so that will be nothing. This will be equaling down to viscosity over mass diffusivity constant from A to B over viscosity, or not viscosity, sorry, density. And this is going to be your Schmidt number. And really, the Sherwood, Peclet, and Schmidt number, really, they're just the names of the people that made this first. They were the first ones to do it, so they get to name it after themselves. That's really all it is. But really, so now we have the dimensionless groups for Sherwood, Peclet, and Schmidt numbers. And the only issue we have left is that we need to get it in terms of the Reynolds number. That's what it is. I always know it's RE, I just can't remember. I have to sometimes forget the names. So yeah, we need to get this in terms of the Reynolds number. And really to do this is we need to take pi 2, which is the Peclet number, and divide that by pi 3, which is the Schmidt number. So if we take this, pi 2 over pi 3, and really how we're going to do that is because we'll be doing this multiplying or dividing by, both of them are fractions or quotients of themselves. We will be doing KCF method. Always want to call it KFC, but it's KCF, keep, change, flip. And so we'll keep the first value, velocity, diameter, mass diffusivity constant, multiply that by the reciprocal of the Schmidt number, which is mass diffusivity constant, density over the viscosity. So these two will cancel out, and we will be left with velocity, diameter, density over the viscosity. And that is actually perfect because that is the exact the function and equation that we need to find whatever the Reynolds number is at the time. And so now that we have the Reynolds number, the Schmidt number, and the Sherwood number, the last thing we really need to do is go through and code and find out use the problem using these dimensionless numbers. And really the end all be all is it's going to be an exponential type of function, where we are going to be looking at it in terms of Sherwood is equal to some coefficient A multiplied, I think it's the Reynolds number first, Reynolds number to the power of B, and the Schmidt number to the power of C. And this is what we'll be looking to try to find and accomplish in the coding part of the section. Thank you, and I'll see you in the next part.